Good evening, everyone. Today we have a great pleasure to have Professor Scott Sloan come here to give us ranking lecture, the 51st of ranking lecture. And Professor Scott Sloan is a university laureate professor and the founding director of the ARC Center of Excellence of Geotechnical Science and Engineering. Okay, he's my postdoc advisor and also good friends of mine. I mean, back 14 years ago, time flies. Right?
Yeah, well, I'm telling my age.
Professor Sloan is an elected fellow of the Royal Society, the Royal Academy of Engineering, Australian Academy of Science, and under the Academy of Technology and Science and Engineering here. And he was invited to just give this 51st ranking lecture, arguably the most distinguished, lectures, recognitions for anyone working in geotechnical engineering here. So we have the pleasure to have Professor Sloan to have an updated version of his ranking lecture tonight. Okay, it's a good chance for us to really to learn more. And Professor Scott Sloan is established a absolute authority in the computational geomechanics and have a lot of recognized awards. And I'm not going to read all of them, otherwise I use 2 hours, the whole 2 hours for his award. And the most recognized one would be the 12-foot medal and 12-foot premier from the ICE, as well as the E.H. Davis lectures on the Australian geomechanics. Okay. And Professor Scott Sloan is an editor of the International Journal of Computer Geotechnics. It's one of the top journals in our field. Okay, and he has been holding a visiting professorship at MIT and UPC. He's one of the world's most highly cited geotechnical researchers, and his research in the field of computational stability analysis, nonlinear finite element method algorithms, geotechnical analysis, and the modeling of unsaturated soil behaviors, nonlinear optimization method, and those are all well regarded. Okay, without further ado, and please join me to welcome Professor Sloan for his lecture.
Thank you very much, Mr. Chairman, and I hope I can live up to that hype. I'd first of all like to thank the IAS and also the Department of Civil and Environmental Engineering for inviting me here to give this lecture. It's certainly a great honour and something I've been looking forward to. As Jidong mentioned, this is an updated version of my ranking lecture on geotechnical stability analysis, and it's basically describing work that's been done in the ARC Centre of Excellence for Geotechnical Science and Engineering at Newcastle since the mid-1980s. So this is work that's been, it's not an overnight success, it's taken a while to get there. And the format of the talk will be as follows: introduction and background, and then I'll give a very brief summary of current approaches to stability analysis, and then I'm going to describe these new techniques, and by new I mean in the last 20 or 30 years that have been developed, which were pioneered for computing upper and lower bounds using the finite element method. These methods are very different to a displacement finite element technique, and I'm going to spend about 20 slides explaining how they work. I'm then going to show how we solve the resulting optimization problems in one simple slide, and then show how we can get an exact error estimator so that we can get a very effective mesh refinement procedure so we get very close upper and lower bounds. Then I'm going to do some applications for undrained stability analysis. Then I'm going to look at the implications of an associated flow rule. For high friction angles, there's always a question: can we use these techniques for those types of soils and or geomaterials in general? Then I'm going to do some drain stability applications, then look at slope stability where we incorporate pore pressures. This is a very recent development, and then finish up with strength reduction for materials with high friction angles, and then some conclusions. Okay, well, geotechnical stability analysis, it's used to predict the ultimate load capacity of geostructure. Once we have that, we typically apply a safety factor to it or the strength parameters in order to get the allowable design load or working load. Once we have that allowable load, we can use some other technique, such as typically displacement finite elements or even theory, to predict the settlements for the design structure. 4 common causes of geotechnical failure that I think are very important, probably the main ones: inadequate site characterisation, poor construction practice, activity after construction, such as tunnelling in particular, and incorrect method of analysis. These are all very important, but today I'm just going to talk about this aspect here. So why is it important? Well, first of all, we have cost pressures driving the engineering profession to use ever lower safety factors, and the social and economic costs of failure can be enormous and are increasing, as are the legal liabilities associated with failure. There's also a community expectation that, hang on, engineers can put a man on the moon, surely we can design a retaining wall or a tunnel that doesn't collapse. So the community expects us to be able to deal with these sorts of problems involving complex material behaviour. However, we note that major failures still continue to occur, so clearly more needs to be done to develop robust and accurate analysis methods. Excuse me if my throat is a bit froggy. I think I've picked up a bug in China where I've been for the last 2 weeks. Examples of some failures. This is the road south of Sydney. This slip occurred after heavy rainfall. It cost about $50 million to fix that. It had to be completely rebuilt and re-anchored. A Lane Cove tunnel collapse. This was part of a $1.1 billion project in the centre of Sydney. The heading collapsed, causing a depression to occur. This multi-storey building had to be evacuated, and it caused the partial closure of one of Sydney's busiest arterial roads. Energy infrastructure failure. This is the Yallourn open cut coal mine collapse, 2007, 6 million cubic metres of material. That mine was 80 metres high, 500 metres long, and went so far back that it diverted this Latrobe River into the mine, causing partial closure of the mine, 20% loss of Victoria's power supply. Victoria is a state in Australia, a bit like a province in China, and so this was a massive cost and a massive loss to their power infrastructure. Another failure, a Jackup rig failure off the coast of Kuwait, September 2002. This is where one of the legs punched through a stiff crust into a soft layer underneath, started to tilt, and eventually the whole thing sank. $350 million for that rig, and we're getting at least one of these failures every year, quite often two. So we still haven't got our stability analysis right. So let's have a look at current approaches. Limit equilibrium, this is the one you all learn as undergraduates. Limit analysis, some of you will be familiar with this, where we have upper and lower bound theorems and we use analytical approaches to calculate those bounds. Slip line methods, which are related to limit analysis, but we solve the governing plasticity equations using the method of characteristics. I'm not going to say a lot about this method, not because I don't think it's important, but because it's not possible to develop general purpose computer codes that employ it. You can get very important solutions out of them, and you'll see some of them in this talk. And last but not least, nonlinear displacement finite element analysis, which everybody uses in lots of different areas in geotechnics. So what are the key things about limit equilibrium? You have to postulate a failure mechanism in advance, and it could be a circle or a wedge or some other shape. You then optimise that geometry to get the critical safety factor. Huge number of methods developed. Some of those are listed there, typically based on very simple soil models, such as Tresca or Moore-Coulomb. Most of the methods are based purely on statics, not all of them. There's one or two important ones that aren't, but generally we tend to ignore the kinematics, and assumptions are required to make the problem statically determinate. And because equilibrium is satisfied globally, but not locally, we tend to get endless discussions about my limit equilibrium method is better than yours. And being the editor of a journal, I still get lots and lots of papers on this theme. Conventional limit analysis. Okay, it's founded on the upper and lower bound theorems of plasticity. We assume a perfectly plastic material with an associated flow rule. So this is the stress-strain response that we assume. So the strength is typically given by this cohesion and this friction angle phi. The yield surface in stress base typically looks like this, and we have these plastic strain rates, epsilon p being normal to the yield surface. So that's what we mean by associated flow. The plastic strains are associated with the yield surface. The gradient of the yield surface, dft sigma, I'll write as grad f through the rest of this lecture. And we have a plastic multiplier, which is non-negative, and we have this consistency condition here that must be satisfied. That basically says that the only time you get plastic yielding is when you get on the yield surface and you stay on the yield surface. Anything inside the yield surface, you have non-plastic deformation. Okay, the lower bound theorem, all we do is we forget about kinematics. We find a statically admissible stress field which satisfies three things: equilibrium, the stress boundary conditions, and the yield criterion. You can have stress discontinuities, and a stress discontinuity is a bit of an abstract concept, but it's basically a discontinuity where the shear stresses are continuous and the normal stresses are continuous. But if you take a plane at right angles to the discontinuity, then the normal stress on that plane can jump. And you can show from statics that such a field will be in equilibrium. We know from the lower bound theorem that if we find such a stress field, we get a safe estimate of the limit load, and that moreover that although the true limit load is unique, we can prove that, finding the best stress field is hard, particularly for complex practical problems. And what we're going to do is describe methods that do that automatically. Upper bound, we do a completely different approach. We ignore statics altogether. So we just focus on kinematics. So the only thing we look at here is we find a velocity field which satisfies the flow rule and the velocity boundary conditions. And I should point out here, engineers often have trouble thinking about velocities instead of displacements and strain rates instead of strains. The reason we talk about rates is because for our ideal material at collapse, the strains and the displacements are uncontained. So you are not undefined because they can be infinite. So if you talk about rates, everything is well defined. In our velocity field, and I should say, if you have trouble thinking about rates, if you want to think about a plastic strain rate, just think of a very small strain increment that's occurring over a very small time step. Same thing. Velocity discontinuities, we can have those. So we can have a jump in the normal component of the velocity and the shear component. That's just like a direct shear test, if you like. Same thing. And the thing that we have to remember, though, is that they must satisfy the flow rule. So for a more Coulomb condition, the normal velocity jump is related to the shear velocity jump by the friction angle, the tan of the friction angle. And we have that absolute value sign because you get energy dissipation regardless of the direction of shearing. Once we have our kinematically admissible velocity field, we equate the rate of external work to the rate of internal energy dissipation due to plastic shearing, and that gives us our upper bound. And again, finding the best velocity field is hard. We have a uniqueness theorem. We know that the limit load for that velocity field is unique. Let's just look at a very simple example. Strip footing, saturated clay, obeying the Tresca yield condition, weightless, undrained shear strength, SU. So what we want is this bearing capacity, QU. Here's a very simple lower bound calculation. We have these two vertical stress discontinuities going down at the edges of the footing. These stresses throughout the domain are constant, and we have zero shear stress because we've got zero unit weight. This stress field out here is the same as that one there. So first thing to note is that we satisfy the boundary condition along there with this minor principal stress. We can have a major principal stress equal to 2 SU because of the Tresca yield condition. Now, as we move across this stress discontinuity, the normal stress must be continuous. So the minor principal stress in this zone here must be equal to 2 SU. And then again, using the Tresca condition, we can have a major principal stress underneath the footing of 4 SU. So with that very simple calculation, we have a lower bound of 4 SU on the bearing capacity. Let's do an upper bound of the same problem. We've got our sector here of rigid material, and outside that zone that's rotating around this point O, directly above the edge of the footing, with an angular velocity of omega dot, there's no plastic deformation. So the only dissipation that occurs, energy dissipation, is due to plastic shearing in this discontinuity. We know that the rate of external work is simply the force times the velocity in a direction normal to that block, and you can show with a bit of mathematics that that's equal to that term. That's the force. The rate of energy dissipation is just equal to the integral of the velocity jump, and we know that that must be r omega dot because that's the tangential velocity just inside this discontinuity, and of course it's 0 outside. So we just integrate that expression over the length. So that's the velocity jump and that's the length, and we equate that to that and then minimise with respect to theta. So we end up with an expression for QU, and we get a value of 5.52 SU. So that very simple calculation, we've established that the limit load must lie between 4 and 5.52 SU. You take the average of that, it's about 7% below the exact solution of Prandtl of 2 plus pi, or 5.14 SU. Now, these techniques are very powerful, but they're a bit of a bear to apply to practical problems because you can't always get good solutions, and we're going to develop methods that do it automatically. Nonlinear displacement, finite element analysis, we'll be talking a little bit about this. 2 ways you get the limit load. The first one is you just apply the load, you keep incrementing it, you plot up the load deformation curve, and hopefully your load deformation curve asymptotes towards a collapse load. It doesn't always do that, and so that can be a problem. The other way that people often use these techniques is you use strength reduction. So what you do is you start off with your actual applied loads and your actual strength parameters, and you keep successively reducing those strength parameters or increasing them in some cases until you cannot maintain equilibrium, usually reducing. So that is another way of getting the collapse load. So you're looking at the safety factor on the strength. Advanced soil models are very possible. You can model all these sorts of features. You can handle soil structure interaction, coupled formulations with consolidation and dynamics, as well as large deformation. However, for stability analysis, my experience is that this is not a method for people who don't really understand the finite element technique, because you're really pushing the method to its limits here when you try and use it for stability calculations. And there have been lots of cases of disasters like the Nickel Highway collapse in Singapore, and numerous others where people have got it wrong because they didn't know how to do the FE calculations. So let's have a look at all of these different methods, comparing limit equilibrium, conventional limit analysis, and nonlinear finite element analysis. In this table, green is generally good. So we see that the nonlinear FE technique is the only method that doesn't require us to presuppose a failure mechanism. It finds it automatically. The lower bound method is the only one that satisfies equilibrium everywhere. In displacement FE, you only satisfy equilibrium at a weak sense in the nodes, at the nodes. In terms of the flow rule, only a rigorous upper bound solution satisfies the flow rule everywhere. In finite element calculations, you only satisfy it at the integration points. Generally, conventional limit analysis and nonlinear FE have the most powerful capability for handling different loading and boundary conditions, and nonlinear FE is certainly the method of choice for implementing complex soil models. The other two are restricted to fairly simple models. So they're the advantages and disadvantages, if you like, of all these different techniques when we're looking at stability. And what we're going to describe is this finite element limit analysis, which is now commonly called Fela. It provides rigorous bounds, upper and lower on the loads. No prior assumptions are needed about the failure mechanism. It's based on finite elements, so you can handle general boundary conditions, loadings, and geometries. It only requires the strength parameters, which is good for practical engineering because that's what engineers tend to know best. They know the deformation parameters with much less certainty. You can model heterogeneous and anisotropic behaviour. The methods are naturally discontinuous. You've already seen that with our simple example. So you can model fissured or jointed materials and interfaces, and you'll see in our examples where we do this, and you can get formulations for both 2D and 3D. So you get the best of both worlds with this technique. You get the power of the FE technique, but you have these inbuilt upper and lower bounds, so you have an idea of what your errors actually are in the solution. Okay, I'm now going to spend about 15 or 20 slides explaining these methods because they are very, very different to the displacement finite element approach. So this is what we typically have. We have our soil volume V. We might have some fixed surface traction, so that might be a ground surcharge T. We might have fixed body forces G, typically unit weights. And what we wish to optimise is some unknown, some distribution of stress, which might be the bearing capacity, for example, and also subject to some fixed boundary conditions, W on the velocities. And the stresses in this domain must satisfy the yield condition. So they're the quantities we wish to optimise, Q and H, and they have very physical meanings. You've just seen them for that simple footing problem. Now in the lower bound, what we typically have is an integral that looks like this. So that's the load supported by the boundary stresses that we're going to optimise, and this is the load that is supported by the body forces that we can also optimise. And the stress field must satisfy the three lower bound conditions, and the load carried by that stress field gives us a rigorous bound. So all of these methods give rigorous bounds, not approximate, but rigorous bounds. So how do we do it in finite elements with the lower bound? Well, we introduce a finite element approximation to model the stress field, and then we optimise that stress field to give the highest lower bound. So let's have a look at the type of element that we use. In 2D, it's this three-noded element, three unknown stresses at each node, and two unknown body forces, typically unit weights, in the X and Y directions. And in 3D, we have this element here, based on a tetrahedron. And we've got linear stresses and constant body forces. So here's a typical grid, that simple example that we looked at before for our footing. We have axis of symmetry down the middle, and what we wish to do here is optimise the distribution, linear distribution of this stress. We only have a linear distribution because we've only got linear distribution of stresses in the elements. And we wish to optimise that stress there to optimise the load. In this case, it's the load acting vertically downwards. Now, all of the stresses must satisfy equilibrium in all of these brown elements, so they're the solid elements, as well as the discontinuities. So these discontinuities are these white elements shown there. And we must also satisfy the stress boundary conditions at those nodes there, those nodes along there. And the stresses at every point inside this domain must satisfy the yield condition. Now, the two things to note straight away: each node is unique to a particular element, very different to displacement finite elements. Not only that, but we have multiple stresses, multiple nodes sharing the same coordinates. That's a bit disconcerting because at any particular coordinate, you may have a multiplicity of stresses. It's not the standard approach that we have in continuum mechanics. There's the face I recognise. And so that's very different mesh to what we normally have. Fundamentally different to displacement finite elements. So how do we express the load in terms of the Cartesian stresses? We know along an element edge we have these local components Qn and Qs, normal and tangential to the edge. We have a linear variation. Because we have a linear variation, we can calculate the load Qn and Qs just by multiplying by the length and taking the average. And these local applied tractions that we're going to optimise are related at each node to the Cartesian stresses by the standard stress transformation relation. So these are the unknown stresses. We feed these equations into there. We can express these loads purely in terms of those unknown stresses, which we then optimise to maximise the load Qn or Qs or both. And we can have very complicated series of edges. The only restriction we have is that over each edge, they're piecewise linear. How do we handle continuum equilibrium? We know that in each triangle, that's there the two equations of equilibrium in the x and y directions, remembering that G is a fixed body force, so that might be a fixed unit weight. H is a body force that we may wish to optimise. And the stresses are varying in a linear fashion. So they're the two equations. We know that we have a linear variation of stress, which is given by this simple equation here, where Ni are linear shape functions. Now, these shape functions are purely a function of the nodal coordinates for the element. So we know those shape functions, we feed them into that equation there, so that gives the Cartesian stresses, sigma x, sigma y, and tor xy. So we feed that equation into there, differentiate, and we end up with this simple matrix equation here, where this is a 2 by 9 equation. And this vector, which is the vector of unknown stresses for our triangle, is a 9 by 1 vector. Now these matrices here, anybody who's done finite elements will know that they are in fact the strain displacement matrices. And they're the strain displacement matrices for each particular node, and we just take the transpose. And they're purely functions of the coordinates, so they're constants. So that's the set of equality constraints that we must satisfy. We know those terms, we know G, so that's a 2 by 1 vector. We don't know sigma and we don't know H. Now it turns out that rather than apply that equation, what we do is multiply this equation by the element area, and we get these equations B bar, which are just the strain displacement matrices multiplied by the element area. And they're equally applicable, and you'll see why we do this in a minute. So they're the equations that we apply, and we have 2 of those for each element. Let's have a look at our stress discontinuities. So what we've got here is our standard triangles, and you saw those white elements before in our grid. They're comprised of 2 discontinuity elements, D1 and D2. Now these elements will be treated exactly the same way as the standard continuum elements. But what we do is we let these nodes 1 and 2 and 3 and 4 collapse to the same coordinate. So this distance here goes to 0. Let's see what happens when you do that by looking at what happens for D1. That's the equilibrium equation we had on the previous slide, where we'd multiplied both sides by the element area. That equation is valid regardless of this distance delta, so that can go to 0. We end up with this equation here, so B2 is equal to minus B1, B3 goes to 0. You grind through the maths and you get this relationship between the stresses at nodes 1 and 2. You grind through that even further, and that just gives you continuity of the normal stress and the shear stress at nodes 1 and 2. Exactly what we need for equilibrium. You do the same thing for discontinuity element 2, and you get the same relationship for the normal and shear stresses at 3 and 4. Because we've got a linear variation, we satisfy it at the endpoints, we satisfy it everywhere along the domain. So the real trick here is that we end up with 4 of these equality constraints by imposing this condition at each of the 2 nodes. And we don't need to make a distinction between the solid elements and the discontinuities. We just let those continuity nodes collapse, and we automatically satisfy discontinuity equilibrium, as well as satisfying equilibrium in the solid elements themselves. So that's a very neat way of implementing it. Stress boundary conditions, like we have these fixed tractions, so that, as I said, might correspond to a ground surcharge. We have the shear and normal components of each of these nodes. They're related to the Cartesian stresses by the stress transformation relation. So we have one set of equations at that node, another set at that node. So we have 4 equality constraints per edge to satisfy a general linear variation. Yield conditions. We've got to satisfy the yield condition at every point inside these triangles. How do we do it? Well, first of all, we know that this yield surface is convex. We know that we have a linear variation of the stress, so we only have to satisfy the yield conditions at the nodes. We automatically satisfy equilibrium at every point inside, automatically satisfy the yield condition rather at every point inside that triangle. So we have 1 inequality constraint per node. Boundary interfaces. What about how do we handle a boundary interface where we might have a different yield function that we want to model? And you'll see an example of this where we look at some quite complicated ones. We simply use those collapsing elements again, but we specify a different yield function at the nodes, say adjacent to this footing or some other retaining wall or whatever. So we can handle interfaces. Now when you go through and sum all of those things up, you end up with this rather ugly looking problem here, which is this is the objective function. We're going to maximise that, and that's the collapse load, and that's the load supported by the boundary stresses. That's the load supported by the body forces that are unknown. Now all of these coefficients C1, B1 and all the A matrices are simply functions of the nodal coordinates, so they're constants. So what we do is we maximise that load subject to the equilibrium conditions in the elements, discontinuities, the stress boundary conditions, and we have one of those yield inequalities imposed at each of the nodes. Now these optimization problems can be huge. We regularly solve problems with millions of nodes and millions of constraints. And you'll see some of the grids later. And the reason that we can solve these things very efficiently is because of the advances in optimization. So that's the lower bound, the upper bound. We forget about statics, we're on to kinematics. And what we do is we minimize this quantity W. Now, that quantity is there is just the dot product of the stress by the plastic strain rates. That's just the plastic dissipation. So that's the rate of energy dissipated due to plastic shearing. We minimize that, but we have to subtract off the rate of work that might be done by any fixed tractions or body forces. And these strain rates and these velocities must satisfy the flow rule and the velocity bound conditions. Once we've minimized that, we equate it to the rate of work done by the unknown boundary stresses Q or any unknown body forces H. Just like we did for that footing problem. Remember, we calculated what the external work rate was, we calculated the energy dissipation, we equated them, and then we minimized it. So that's all we do. We use finite elements again, but this time to model a velocity field. So in 2D, we have these triangles, 2 unknown velocities in the x and y directions, and we introduce a constant stress field in our upper bound. We don't have to do this, but the reason we do it is because it provides a very easy way to calculate that dissipation, because remember, we just want the dot product of the stress times the plastic strain rates. And it also allows us to calculate an exact error estimator, which you'll see very shortly. 3D, tetrahedral elements with these unknowns associated with the nodes and the unknown stresses at each element. So the velocities are linear, but the stresses are constant. Here's our simple footing problem again, axis of symmetry. What we typically do for our rigid footing, we impose a unit downward velocity on our rigid footing, and then we go about minimizing the rate of internal energy dissipation throughout this domain here. And the velocities in each of the triangles must satisfy the flow rule. The velocities in each of the discontinuities must also satisfy the flow rule. And the velocity boundary conditions around the edges here must also be satisfied. We have a fixed stress associated with each of these brown triangles that must satisfy the yield condition. Just like the upper bound, these grids are very different. We have each node is unique to an element, and we can have multiple nodes sharing the same coordinates, which means we can have multiple velocities at a single point in space, which is a bit disconcerting when you're used to displacement finite elements. So this is the thing that we're going to minimize. So we're looking at the objective function here that we're going to minimize. This is the power dissipation. This is the rate of work done by the fixed tractions and the body forces G. Look at this term here. We know the stresses are constant. So for each element, we can reduce this integral to this triple dot product here because this plastic strain rates are constant. You've got a linear variation of velocities. So we know that the plastic strains are related to the unknown velocities for the triangle by the strain displacement matrix. So we end up with this triple product there to get that, and we can express that also using those B bar matrices that we had for the lower bound, where B is just the strain displacement matrix multiplied by the element area or volume. These terms up here, if you grind through the maths, you know a linear variation of T, you have a linear variation of U. We have fixed body forces. You can evaluate these integrals, and that simply reduces to a term that looks like this. So this vector U is just the unknown, vector of unknown velocities for the triangle. So we have 6 of those for our 2D case, and C is just a vector of constants. So they're the things that minus that is what we're going to minimise. The flow rule, we know that our velocities vary in a linear fashion using those linear shape functions. So they just give ux and uy at each point. So we feed those into these equations and then do the differentiation, and we end up with these equations that look like this. So that the plastic strains are given by the strain displacement matrix by the velocity for the element, and they're the equations that we impose. So we impose that condition, B times U is equal to that right-hand side, and this vector here is a 3/1 vector. It's just the derivative of the yield function with respect to sigma x, sigma y, and the shear stress. We have a non-negativity constraint on the plastic multiplier. Remember our flow rule, and we have the consistency condition that must be satisfied. So they're the flow rule conditions that each triangle must satisfy. So what we can do is use that trick again where we multiply all of these equations here by the element area. So these plastic multipliers in fact become alphas. So they're the equations that we impose. So we have 3 nonlinear equality constraints in there, 1 nonlinear equality constraint there, and 1 inequality constraint there. So we have overall 4 nonlinear equality constraints, 3 there, 1 there, and 1 inequality constraint that we must impose. Now, as you'll see, we handle discontinuities in the same way. We just have 2 of the standard elements, and D1 and D2, and we let these nodes 1 and 2 go to 0. Because the flow rule is applicable for these equations here, regardless of the element area, if you grind through the maths, you can show that at nodes 1 and 2, with a Moore Coulomb condition, for example, you get a relationship between the normal and the shear velocity being equal to that. And similarly, at nodes 3 and 4, you end up the same thing with D2. So you satisfy the velocity jump across the triangles, across that discontinuity rather, and because you've got a linear variation, you satisfy it everywhere along the element edge. So you end up, you have to apply those conditions, 3 equalities and 1 there and 1 inequality at both nodes 1 and 2. So you end up with 8 nonlinear equality constraints and 2 inequality constraints. Yield conditions, we have a constant stress. We just impose that the stresses must lie inside the yield surface for that element. Interfaces, we can impose a different interface condition, and we'll give an example of that using those 0 thickness elements again. And that's what we end up with, this rather ugly looking optimization problem. Sigma is unknown, U is unknown, and these alphas, which are related to the plastic multipliers, are also unknowns. So that's the energy dissipated due to plastic shearing. That's the first term, and this is just the rate of work done by any fixed loads. These are the flow rule conditions. They're the velocity boundary conditions where we know A and we know B, and that's the yield condition. Again, these nonlinear problems can be absolutely huge, millions of unknowns and millions of constraints. Right, well, that's all very well and good. That's how we formulate them. Hopefully you can get an idea of how different they are to standard displacement finite element techniques, but how do we solve these optimization problems? Well, we choose an optimization solver depending on the type of yield condition. So if we've got a Hook-Brown, if we're doing rock mechanics problems, we can use a quasi-Newton type of solver. If we've got von Mises, Drucker-Prager, or 2D Moore-Coulomb, we can use a technique called second-order programming. These techniques are very fast, and they can handle discontinuous yield surfaces. And if we have 3D Moore-Coulomb, we use semi-definite programming. And the last little bit of theory for a while, how do we adapt the mesh? Now, we've got our mesh and we've got our upper and lower bounds, but how do we know that we're actually going to get decent upper and lower bounds? The methods are useless if we can't get close bounds. Well, it turns out that we use the same mesh for the upper and lower bound calculations. We don't use different meshes. And it turns out that if you do that, you have an exact estimate for the contribution of each element to the gap in the upper and lower bounds. And that contribution is given by this delta quantity, so that's just the dissipation. We know that for each element, we know the stresses, and we know the plastic strain rates from the upper bound. We do the same thing for the lower. We use the upper bound strain rates, but we use the lower bound stresses in this, and we derive this equation. I'm not going to do it, but we use the virtual power theorem, and we can show that for a unit rate of external work, if we sum those delta quantities, we get a direct estimate of the gap between the upper and the lower bound. So how do we make a fast solution? We make the size of the elements inversely proportional to those delta quantities. That's the only nonlinear problem that I know where we've got an exact error estimate. Okay, let's have a look at these things. We looked at Davis and Booker problem, plane strain, strip footing, Tresca, strength increasing with depth. Undrained shear strength at the surface SU0, rate of strength increase with depth rho. Davis and Booker showed that you can express the bearing capacity using this equation here. So that's the Prandtl type of contribution, and this is the contribution due to the strength increase. This factor F depends on whether the footing is rough or smooth. So what we did with our upper and lower bounds, we thought, well, this is a good test case to look at because Davis and Booker provided some solutions from the method of characteristics, and these solutions have been very widely used in practice. So what we've got here on this axis is F, noting that we've got a false origin here because it starts at 1. And we've got two curves, one for the rough, one for the smooth. And this axis along here is the dimensionless strength, and it flips over halfway along. So it's rho B and SU up to there, and then we take the inverse for the rest of the plot. Why do we do that? We can put all of the cases on one particular plot. So at this end, we have the case where we've got a uniform strength, and at this end of the plot, we have a case where we've got a zero shear strength at the surface. So when we did this, we got our upper and lower bounds, as you can see by the red and the green symbols, and we thought, well, that's very comforting. Our upper and lower bounds typically differed by plus or minus 0.5%. The only problem was they didn't agree with the solutions from the Davis and Booker published results that we used very widely. So we looked for bugs in the code. We spent about a month and a half looking for bugs. We couldn't find any bugs. We were very confident that the results were consistent because we had such tight upper and lower bounds. So I contacted Chris Martin at Oxford, who had written a method of characteristics, a program which used adaptive meshing for this particular problem called ABC. We reran that problem with his characteristics code, and we got results that were right in between our upper and lower bounds. So that method, just that simple example, shows how important it is to be able to have that check on the upper and lower bounds. It tells you if there's something wrong. And we subsequently showed that these upper and lower bounds from Chris's program are in fact exact solutions. So these are the exact solutions, and we're getting very good agreement with our upper and lower bound results. Just to show you this adaptive meshing, this is where we calculate the bounds gap for each element. We start off with a very crude grid, 100 elements. We restrict the number of elements to 2,000, simply because if I don't, this thing here will turn into a black blob and you won't be able to see any of the elements. Pretty awful upper and lower bounds to start off with this grid. As you'd expect, it's not very refined, 77% difference between the upper and lower bounds. And then we start using the adaptive meshing, where we're using the same mesh for the upper and lower bounds. You can see that after about 3 to 4 iterations, we've nailed the exact collapse load within plus or minus 1%. And that's a fairly typical approach or characteristic that we get with these solutions. That total time, I think, was about 45 seconds on a laptop to do all of those analyses. And as you can see over here, you're getting big concentrations of elements exactly where you'd expect. We compared our limit equilibrium solutions or limit equilibrium solutions from Raymond with our finite element limit analysis solutions. These are also very widely used, and they're based on a circular failure surface. And we've got this ratio between the limit equilibrium and Fela results. And as you can see, for the case where we have a uniform shear strength, the limit equilibrium results are all right. But for the rest of the plot, they're typically out by factors between 2 and 4. So the limit equilibrium solutions are absolutely terrible for this case, even though they're theoretically rigorous limit equilibrium solutions. And in fact, for the case where you have zero shear strength at the surface, they're 4.5 times what they should be. Well, why is this? You look at the failure mechanisms and look at the one on the right-hand side here. I've plotted up the power dissipation from our upper bound calculation. This gives a very visual indication of how these things fail. And what you can see is for the case where you've got a very low shear strength at the ground surface, the soil's just being squeezed out from underneath the footing. You're not getting a deep-seated failure mechanism at all. And you compare with the Raymond analytical failure surface, it's miles off. It can never, ever get the exact solution. And that's the problem with limit equilibrium methods. You never know how good they are unless you have some other thing to compare them with. These upper and lower bound methods, we get it straight away. So that's the Davis and Booker problem. Let's have a look at a problem that I did with our colleagues at MIT. We were looking at combined loading of footings, again on a Tresca material, this time uniform strength. We have an eccentricity of 0.45b and a ratio of the horizontal to vertical force components of 0.2, and we produced envelopes for a wide range of these parameters. And what I'm going to look at is 3 different interface conditions along here, because that's what we often want to do in practice. And this first interface condition here, this is just your standard soil mechanics plot of shear stress versus normal stress, and that black line there is just the standard undrained failure envelope yield surface. So that's just assuming that we have a Tresca interface, so it can sustain both tension and shear being equal to, as provided the shear stress is less than the undrained shear strength. This one over here is the same as that, except we've put a tension cutoff. We're not going to allow any tension to occur normal to that interface. That's the case that you'd like to model. Now these red arrows and red symbols there, they're the velocities, and you see in this, they just tell you which direction the velocities jumps must occur. So in this case, you can see the only shear deformation, the only deformation that you can have is in the shear direction along that interface. This one says that you can have a whole range of them. This case is a rather interesting one. We said, okay, we're not going to put any constraint on the shear stress on this footing. We're just going to insist that we don't have any tension. And that is just a single line. So the admissible stress space is over here. And you see for this case, because you've got associated plasticity, all the velocity jumps must be normal to that interface, in the same direction as sigma n. Okay, here are the upper and lower bound results. Firstly, we note that the upper and lower bounds are very close together, typically about within plus or minus 1.5% with 3,000 element grids. They typically took about 35 seconds to calculate each of them. The cohesive case, so that's where we've just got the Tresca interface, we get that expected type of failure mechanism. when we have the no tension, we get this separation and we get the failure mechanism going halfway across the footing. These are quite difficult calculations if you want to do them with a conventional displacement finite element method. You have to go into contact mechanics. They're really messy, believe me. And this is the case where we had no tension, but we didn't restrict the shear stress. We get this very interesting sort of double failure mechanism. So, very simple way of imposing fairly complex conditions that we have in practice, and the case where we had the one that's most realistic, where we had cohesion but no tension, gives a limit load which is about 19% less than the case that most people would assume when they're doing these analyses in practice. Tunnels and tunnel headings. What we have here is strength increasing with depth, again with an undrained shear strength SU0. We've got our circular tunnel, cover C, diameter D, and we've got a ground surcharge. What we typically have in tunnel construction is we put in a lining as the tunnel is constructed, but this heading length here, which doesn't have a lining on it, is supported by some internal tunnel stress which is assumed to be uniform. And what tunnelling engineers need to know is what value of sigma t is necessary to prevent this thing caving in. Noting that you can't have sigma t too large because you can cause blowout. You can get the opposite effect. So this unsupported length is P, and if P is much, much greater than the diameter D, you can treat this as a plane strain problem. You can just take a section through like that, and that's the one that you often see in the literature. By looking at the work equation, you can show that the stability number for this case is simply given by this, the difference between the surcharge and the tunnel stress divided by the undrained shear strength. We typically normalise with respect to the surface, and you can show it's a function of these geometry parameters, C on D, P on D, this dimensionless weight parameter, and this dimensionless strength parameter. 2D case first. This is some work that a PhD student of mine did, and this is for the case where P on D is much, much greater than 1, so we're treating it as plane strain. This is the stability number, this is the dimensionless weight parameter, and these are the curves for various values of the strength parameter. So that's the uniform strength case, that line there, and that's the case with the maximum strength increase with depth. So how would tunnelling engineers use something like this? Well, first of all, I should say that the upper and lower bounds are virtually indistinguishable. And this is for a case of C on D on 4, and we did a whole range of C on Ds that are useful in practice. So how engineers would use this, they know what their strength profile is. They know what this dimensionless weight parameter is, so you go in up there, read off what the stability number is. Once you've got that stability number, you typically know the surcharge stress, so you can work out what sigma t should be. Alternatively, if you know what your capacity for the tunnel pressuring is, you can work out what sort of ground surcharge you can support without collapsing. That's the optimised grid for one particular case. As you can see, we're getting all the elements where you'd expect them to be. Power dissipation plots again, one for the uniform strength case, one for the increasing strength with depth. You can see the uniform strength, much larger failure mechanism. You're getting this trumpet type of failure mechanism here, and you're getting a lot of plastic failure below the floor of the tunnel. For the strength increasing with depth case, the tunnel doesn't want to fail in the strong material, so it avoids it, and you get a much more localised failure mechanism. Again, you get this very physical idea of how these things are behaving. We also compared with solutions from Centrifuge results rather from Robert Mayer. This is the stability number for the uniform strength case. He presented his plots in a different way, used C on D for a specific case of this weight parameter, uniform strength. Upper and lower bounds almost identical, and the centrifuge results are shown here. These centrifuge results are widely regarded as being some of the best results that were obtained, and people often use them to check various calculations, and these gave us a lot of comfort. We're getting very good predictions from our upper and lower bound methods with high quality centrifuge tests done at Cambridge. Well, okay, that's good for the 2D case. What about the 3D case? Excuse me. Start croaking in a minute. Here we've got our normalised tunnel stress. So this is for the case where we don't have any ground surcharge. And we plot up that stability number, sigma T on SU, uniform strength versus P on D. Remember, P is that unsupported heading length. As P on D gets large, you go towards the plane strain case. So at this end of the plot, you're at plane strain. First thing, because we don't have a surcharge sigma S and sigma T is resisting collapse, the upper bound calculation actually gives you a lower bound, and the lower bound calculation gives you an upper bound. It'll do your head in if you think about that too much, but that's the reality, because this load is resisting collapse, it's not causing collapse. Whereas that other tunnel where we're taking the difference, that's causing collapse. So we did upper and lower bounds. That's the best that we could get with about 30 to 40,000 elements. Taking the average, you can see that for a P on D value of greater than about 1, we're getting about a 15% difference between the limit analysis solutions and Mayer's centrifuge results. So we were fairly happy with that. We'd like to be able to get these bounds closer, but we've found that for 3D, the theory is great for optimizing the mesh. It doesn't change going from 2D to 3D, but when you try and do 3D optimization, you get disappearing elements, you get slivers. It gets a very hard problem from a practical point of view. The theory is fine, but getting it to work in practice, because you don't have these nice properties that you have with 2D triangulations. But we're certainly working on that so that we can get better bounds for the 3D case. And as you can see, both the upper and lower bounds asymptote towards a 2D case as P on D gets large. So as you end up with a plane strain type problem. The collapse mechanisms, so power dissipation, this is the case with no overhang. So this is, you've got the unsupported length is 0. You get this circular bowl of collapse, which is almost all forward of the tunnel heading. No heave. When you have a much longer unsupported heading length, you get this case where the roof collapses and you get quite a lot of heave. So this is going towards a plane strain type of failure mechanism. Those types of calculations typically took about 3 to 4 hours to get our upper and lower bounds. So we're still working on that, but it's if we could get the adaptivity going, we'd be able to get better bounds for less cost. But if you do a 3D finite element calculation, you'll probably be doing at least that amount of time and maybe more. Well, that's all very good. So we've given a whole bunch of applications for cases where we've got undrained loading. What about cases where we've got drained loading and we've got a friction angle? So let's have a look at the implications of using this associated flow rule. So this is a bit like a direct shear test where we've got our discontinuity going through there. We know that for an associated flow rule, the relationship between the normal velocity and the shear velocity is given by this quantity tan phi. So that's for a more Coulomb material. And that's the model that we assume in finite element limit analysis. Now, that's a bit of a worry, because we know in practice the actual relationship between the normal and shear velocities is given by tan psi, where psi is the actual dilation angle. So this dilation angle here is often considerably less than the friction angle. Not only that, but as you shear the thing towards failure, that dilation angle can go to 0 as you go towards the state. So that raises the question, we've got completely different assumptions here, our assumptions don't particularly match what we see in practice. What are the implications? Well, clearly it's only an issue for frictional soils, and the big condition is that the predicted limit load, or the biggest worry is that the predicted limit load may be too high if the problem is kinematically constrained. So if you have a hopper flow problem or a cavity expansion problem, you can get a very big difference between the limit load from an associated flow and non-associated. However, many non-associated problems are not highly constrained due to the fact we have semi-infinite domains and a free ground surface, and we know from plasticity theory that we can get multiple mechanisms give the same limit load. So that suggests we have a low degree of kinematic constraint. Well, that still doesn't get us anywhere because over-associated flow over-predicts shear dilation. We can expect problems for soils with high friction angles. Well, Davis, in a celebrated book chapter in 1968, said that, okay, we can tackle these problems by using these reduced strength parameters, C star and phi star, which are related to the actual strength parameters by this quantity beta. And that's just dependent on the dilation angle and the friction angle. How did he derive this equation? He looked at the Moore's circle of failure in a characteristics net for a non-associated flow, and he proved that the shear stress is related to normal stress by those reduced strength parameters there. That gets our strength right, but it still doesn't necessarily get the velocities right, any velocity jumps, because we know that they must be related by this equation here, where that dilation angle psi isn't going to be the same as phi star, which is what we assume. But as a number of people have shown, that that approximation is a pretty good one, and in fact you can show that for a rigid block mechanism where you've in non-associated material where you've only got deformation occurring in the discontinuities, this approach here will give you a rigorous upper bound on the limit load for your non-associated material, and Andrew Drescher and Emmanuel de Tournay proved that in 1990. But we still have problems with non-associated flow with more Coulomb. We know that the bound theorems are no longer applicable. We have a loss of uniqueness, so there's no guarantee of a unique limit load. And if you do displacement finite element calculations, and you'll see some of those problems later, that if you get a big difference between the friction angle and the dilation angle, you can get these oscillating load deformation responses. And not only that, you can get softening, even though you've got a perfectly plastic model, which is a real worry. And you can also get numerical instability. So just to fix ideas and on how these things behave, and just to show you, emphasize this idea of kinematic constraint, we're going to look at a biaxial test. Height of the sample L, width B, rough platens, a short sample, which has L on B equal to 1, and a longer sample, L on B equal to 3. Friction angle 30 degrees and 3 different dilation angles, 0, 15 and 30 degrees, which is the associated case. We know that the actual failure plane is given by 45 plus psi on 2, where psi is the dilation angle. And we know for the associated case, the actual collapse load is given by this simple equation here, provided L on B is greater than 1.73. Why? Because when that failure plane is phi, you must have that length in order to stop the platens from interfering with that failure surface. We first of all analysed this using our in-house finite element code, using the 15 noted triangles. Love them or hate them, they're everywhere in practice. They were developed by me in my PhD thesis and a subsequent paper. And we showed that these elements are extremely good for predicting collapse, whether it's cohesive friction or undrained problems where you have constant volume. So we used a lot of these elements, 800 of them. This is a quarter of the sample for the L on B case equal to 1, the short sample. They were the boundary conditions we applied. For the longer sample, we just repeated that grid 3 times size. And here are the results. Normalised pressure, vertical strain. Just look at these blue curves first, so therefore the long sample. And the striking thing here is that the load deformation response and the collapse load is independent of the dilation angle. That is not what you'd expect until you think about it. The reason is that for all of these cases with the longer sample, the failure plane can choose where it wants to go. So it's not highly kinematically constrained. And you'll see that in a minute when we look at these shorter sample results. The associated case has a collapse load which is about 30% greater than the long sample. Not only that, but the case with zero dilation has a collapse load which is about 12% below the case of the fully associated with. So this is the constant volume. For our finite element calculation, we had trouble. The technique wouldn't work beyond this point, and you can see we're starting to get these oscillations. And you can also see that we're even getting some oscillations in the case with dilation angle of 15. So the take-home message from that is that illustrates the case of the importance of kinematic constraint. If you have a problem that's kinematically constrained, the flow rule is really important. If you have a problem that isn't, then the flow rule is less important on the collapse load. Here are the results. We analysed these problems using our Fela codes, and you can see that we got these meshes here. We reproduced the exact collapse load, very diffuse type of failure mechanisms. For the shorter sample, we got these very concentrated failure mechanisms, and that's because the platins are interfering with the failure mechanism. And we got the upper and lower bound to within about 1%. This plot shows the same results again, but we're just comparing the Fela results with the FE. For the associated case, we're getting very good agreement between SNAC and our Fela codes. For the associated case, non-associated case with a dilation angle of 15, what we did here was we calculated these reduced Davis parameters and then did our normal limit analysis, and we got those results there, red. So they're a little bit, about 4 or 5% below the best estimate that we can get from the FE calculations. Okay, let's have a look at some applications. This is a drained case. It's an anchor in medium dense sand that we're going to look at, and you can show that the pull-out capacity QU is related to gamma H via this factor N gamma, not to be confused with N gamma for footing, and it's a function of the friction angle and this dimensionless quantity H on D. We can't do axisymmetric analyses exactly with limit analysis because of the hoop term. So what we do is we do a three-dimensional slice, and we used a slice of 15 degrees, and we used up to 14,000 elements. So what we thought we'd do is compare our solutions with some laboratory data from chamber tests. So this is N gamma on the vertical axis versus H on D. And these black squares are from a master's thesis from Andrew Pierce for a sand with a friction angle of just over 43 degrees and a dilation angle of 13.6 over the relevant stress range. He got some odd results here, which were later explained by the chamber effects. The values that he used, he'd done the samples too close to the edges. We also looked at some results from Lamperouthia used for circular anchor in sand, 43 degrees, and we got very similar results over most of the range. We then did upper and lower bounds, but we used this Davis approach. So we know that the friction angle is 43.1, we know that the dilation angle is 13.6, so we can use those formulas to calculate beta and get a reduced value of the friction angle. First thing to note, we got nice upper and lower bounds, plus or minus about 3%, and they agree pretty well with the experimental data. We also did some finite element calculations using SNAC, using the exact values of the friction angle and dilation angle, or by exact I mean the actual measured values, and we got that black line there. We had a lot of trouble getting this line because we were getting some really big oscillations in the load deformation curve, so I don't have a huge amount of confidence in it, and we had to do least squares simulations to estimate them, but that's the curve that we got. Key take-home message is that you can use these methods for soils with high friction angles, medium dense sands, and get very good estimates of the limit load, provided you use Davis's approach to modify the strength parameters to allow for non-associated flow. They're the failure mechanisms. For a shallow case and a deep case, you can see the deep case is much more localized, as you'd expect. More Coulomb case, circular excavation, height h, diameter 2r. The dimensional stability number, NS, is a function of the friction angle and H on R. We analysed it using this grid here, 8,000 elements, 15-degree slice. They're the upper and lower bound estimates for this stability number versus H on R. This curve here is for the purely cohesive case, almost identical upper and lower bounds, and no, quite an improvement on the analytical solution obtained by Brito and Kusakabe. For the other friction angle, 10 and 20 degrees, so these are typical values for a silty clay. We're also getting good upper and lower bounds. I think the maximum difference we ended up with plus or minus about 2% in any of those upper and lower bounds. But all of those solutions are significant improvements on these other upper and lower bounds that were provided by Turgeman, after just shown by those dots there. Failure mechanism, purely cohesive case, much more extensive, and is getting this trumpet failure mechanism again for the case where we had a friction angle of 20 degrees, much more localised and much more steep. Now for these cases, when we plot up the failure mechanisms, we contour the plastic strains, not the dissipation. And the reason we do that is we can look at the multipliers, and if you have a purely cohesive or purely cohesionless material, the dissipation is not defined, but the plastic strains and the multipliers certainly are. Okay, so we can undrained, drained, we can solve problems. What about incorporating pore pressures? How can we do it? Well, we've found that you can incorporate steady state pore pressures by solving the governing seepage equation using optimization theory. It turns out that these optimization problems that we've been talking about for the upper and lower bound method can be used to solve the pore pressures. So we end up with a very similar upper and lower bound approach, or similar problem to the upper and lower bound methods, and we use a similar solver. We can find the phreatic surface for unconfined flow, and the pore pressure mesh is the same as the mesh that's used for the upper and lower bound analyses. So we use the same mesh for the upper and lower bound calculations and the pore pressures, and we're going to adapt them all in order to get the solution. Strength reduction is used to compute the upper and lower bounds on the safety factor, and we use a hybrid adaptive meshing algorithm to minimise both the bounds gap, which I explained before, and we also calculate another error estimator which is based on the curvature of the pore pressures in the grid that we use to calculate those. And then we take the minimum element size that we get from those two estimators. So how do we do it? Lower bounds, 2D, we have our same nodal variables as before, except that we have this auxiliary pore pressure that's calculated separately to the upper and lower bound calculations. So we have linear stresses, linear pore pressures, and constant body forces. We impose equilibrium in terms of the total stress as well as the stress boundary conditions, and we make sure that the yield condition is satisfied at each of these nodes using the effective stresses because we've got the pore pressures in there. Upper bound, same idea. We just, for 2D, we just augment this unknown velocity field by a linear variation of pore pressures. And each of the elements, we have these effective stresses, so we enforce the flow rule in terms of effective stress, not total stress, because we've got pore pressures now. And this work term, remember way back when we were describing the upper bound, that's the dissipation, that's the rate of work done by the fixed tractions T and these body forces G. We have to also take off this term that's due to these pore pressures. That's the relevant work term. The gradient of the pore pressure is a constant, so this integral is very easy to evaluate. We just have to integrate the velocities over each triangle, and we can calculate that integral very easily, even if we've got velocity discontinuities. So that's the upper and lower bounds where we've got the pore pressures. How do we calculate the pore pressures? Well, we introduce the same grid, but this time we have unknown heads, And we know that for confined or unconfined seepage flow in an isotropic soil with permeability K, total head is governed by Laplace's equation shown here. Now we can solve much more complicated equations than this, but this is a simple one because we just want to show the method. That equation has typically got to have fixed head, fixed flow conditions on it, and you have a constraint on the pore pressure. So we're going to solve that equation with these boundary conditions shown there. And any of you who have done flow nets will know exactly. Now it turns out that you can minimize this functional here to obtain the unknown pore pressure. So this is the head, the total head, and you solve that optimization problem, that functional there, subject to boundary conditions on the head, flow, and pore pressures. So we have, at the same grid that we use for the upper and lower bound, we also have these another grid that we calculate these heads. We have a linear variation, so we have a single unknown head at each of these triangles, and we use the same mesh as the upper and lower bounds, but we don't have any discontinuities because we don't want to have discontinuous pore pressures. Let's have a look at an example. This is a slope with a weak layer, and this weak layer has 0 effective cohesion as opposed to 28.5, and its friction angle is half. It's clearly going to have a non-circular failure surface, and we've got ponding to a depth of 1 metre here, and we've got about a water table coming out about 2 metres below the crest. That's the optimised pore pressure grid. That's where we solve that optimization problem for the pore pressures, and using our curvature of that grid to get the optimal grid. You can see we've certainly captured this phreatic surface very nicely, and that's the contours. They're the contours of the pore pressure shown there. Check those contours with contours obtained using other methods and got exactly the same result. Here is the grid for the final solution, where we optimize not only the pore pressures but also the upper and lower bounds. So the way we do this, we do an analysis for our upper and lower bounds. We calculate what the element sizes we want. We then do a same analysis where we solve for the heads and then the pore pressures, find out the mesh that we want, and then we choose the one that gives us the smallest element size. So we get the most critical element size for both the upper and lower bounds and the pore pressures. The way that we do the strength reduction is, this is a very interesting example of where we might want to optimize the unit weight. So what we do is we calculate an upper bound for the unit weight, a lower bound for the unit weight, take the average to get this gamma bar quantity, and then we calculate this multiplier, which is equal to the upper and lower average of the upper and lower bounds divided by the actual unit weight. And to get the factor of safety, we want that ratio to be equal to 1. So here's a trial and error approach. This is how we implement it in practice. We started off with a safety factor of 1. You can see that this multiplier was less than 1, so we reduced the safety factor to 0.9. It came out to about 1.5, and then we did a linear interpolation between those points, and we got a safety factor of 0.95. So in 2 iterations, we had our safety factor good to a couple of decimals. You can automate that search procedure very easily, and we've done it. There are comparisons of the failure mechanism for both the case with the water table, and we also analysed it without the water table. As you can see, you get a much more extensive failure mechanism, as you'd expect when you've got the water table. And here are some results for the factor of safety using slope W, and we considered a whole bunch of different techniques, and these results took us a good day and a half, 2 days to get, because we had to cycle through all of the options for each of these techniques. And anybody who's done limit equilibrium will know that you have a very large number of options with these codes. And we've got the Fela results there, and the results that agreed very well with our Fela results were Sama, Spencer, Morgenstern, Price, and they're the ones that are most rigorous because they satisfy both moment and shear equilibrium on the slices. So we were very happy with those results, and we believe that that's pretty close to the exact factor of safety. And we did results for the case with no water table, but I'm not going to include that today. We also did a Plaxis analysis and got a safety factor which was substantially less. And it turns out that Plaxis, when it does its strength reduction, so this is a finite element code, it actually reduces the dilation angle, not just the friction angle. So you're actually solving a different problem, this one, to all of these others, because you've got a different dilation angle. So just because you get a low value doesn't mean it's right. I think that these values up here are pretty close to that exact solution for the case with a weak layer. Okay, the last example that I'm going to look at is strength reduction with high friction angles, and we saw that for our anchor problem we got very nice results using the simple Davis approach for the limit load. Those results agreed very nicely with experimental data, but we weren't using strength reduction because it was a force control problem. What happens when you have strength reduction? Here we looked at, this is more recent work, so here we looked at a gravelly slope, alpine gravelly soil, a slope in alpine gravelly soil rather, a slope angle of 45, and friction angle high, 45 degrees, effective cohesion of 6, and a variety of dilation angles ranging from naught, i.e. the isochoric case, all through 45 degrees where we got associated. So the first thing we did was do a Plaxis analysis. So this is a finite element strength reduction, SRFEA, and we looked at the deformations at this control point. Here are the results. Factor of safety on this axis, again we've got a false origin here, and on this axis here we've got the displacement at the crest as we do these continuous strength reduction iterations in Plaxis. So you can see that for the associated case up here, where the dilation angle is equal to the friction angle, you're getting pretty decent behaviour, not too many oscillations, and we're getting a reasonably reliable estimate of the factor of safety of 1.52. For the non-associated with dilation equal to 15, again we get this drop off there, but then it behaves fairly well. An estimate of the safety factor of about 1.46. However, for the zero dilation case, we get these oscillations. And that is really typical of the sort of things that engineers have to deal with when they want to do a strongly non-associated case. In fact, I've seen oscillations for some other cases that take up to about 30% of the factor of safety. And this causes engineers a lot of consternation. What is the factor of safety from this analysis, and can you believe it? Well, we did a least squares fit along there and came up with a value of 1.32, but put a question mark. We weren't entirely confident with this. We then went back and did some simple Davis analyses, and we got these results as shown by these dots. So for the associated case, where we'd expect to do quite well, we agreed with Plaxis very closely. For the non-associated with 15, we got a result which is about 10% below the Plaxis result. And for the strongly non-associated with zero dilation, we got a 1.1 versus 1.32, which is about a difference, I think 16, 17%. So we were thinking about this and we thought that these differences are rather large, particularly this red one. I'm not too sure what to make of this blue one, but certainly we think that these are fairly reasonable. So because you're not getting oscillations. So we thought, well, maybe we need to revisit the Davis approach, and maybe we need to look at that assumption that we make where beta is held constant. Now, they're the modified strength parameters that we use when we've got a non-associated material. Now, as you can see, beta is a function of phi. Now, if you're doing strength reduction and you've got a high friction angle, beta is not going to be constant. It's going to vary quite a lot. So it makes a lot of sense to actually calculate the most accurate estimate of beta that you have by using your latest value of phi, mobilised phi, that you have in the strength reduction process. So that's what we did using this formula here. So all of these terms inside these arctans there are simply the current mobilised friction angle allowing for this factor of safety that you've applied to it. So we use this formula again, but we have a dynamic estimate for beta, and we do impose a condition that the dilation angle can never be greater than the friction angle, because that doesn't make any physical sense at all. So we check that the dilation angle doesn't exceed the friction angle as we reduce it. If it does, we just set it equal to the friction angle and reduce the two of them simultaneously. That doesn't occur very often, I should add. And you can use this technique for cases where you don't have a high friction angle, but you'll find that the results are not very much affected by it. It mainly has an effect for cases where you've got gravel or you've got a medium dense sand where you've got a high friction angle. That's because the way strength reduction works. So here are some results for our slope. That's the simple Davis approach that we used for our anchor, and that's the modified Davis where we adjust beta as we do the strength reduction. And as you can see, it's typically giving values of the safety factor which are about 8 or 9% greater than the standard Davis approach. We then compared the results from these two Davis methods with Plaxis and calculated the percentage difference, and as you can see that the modified Davis approach does give results that agree pretty well with Plaxis, certainly for dilation angles that are fairly realistic of 10 or 15 degrees. These values here, I'd sooner trust the limit analysis results than the finite element results, simply because you're getting those oscillations and you don't really know what the true safety factor is. So the take-home message from that is that this modified method does allow you, Davis method does allow you to deal with soils with very high friction angles if you're doing strength reduction, and you'll avoid a lot of the problems that you have with displacement finite elements when you're doing strength reduction in practice. Okay, so to wrap up, I think that one of the key conclusions is that this finite element limit analysis technique is a very powerful new tool for stability in both 2D and 3D. It doesn't require the deformation parameters, just the strength parameters. They're the parameters that engineers know the most and they're very happy with, and they're very simple to apply in practice. You can handle very complex conditions, such as those conditions given there. That bounds gap indicator allows, for each element, allows you to get a very robust and efficient mesh adaptivity procedure, simply because it's calculating the contribution of each element to the gap between the upper and lower bounds. The methods are ideally suited to strength reduction. You can use that technique that I showed you for the slope. You can just do a stepping procedure, and it's very easy to do strength reduction. It's not so easy to do in displacement finite elements, I can tell you, because there are a number of tolerances and convergence problems that you have to deal with. Think about it, displacement finite elements, we normally want convergence. That's what we ask, that's what we're looking for when we do nonlinear problems. With strength reduction, you're looking for the problem where it doesn't converge. So good luck getting that accurately. There are a whole lot of arguments about how do you know when something hasn't converged. Whereas with the limit analysis methods, you deal with it straight off. Not a problem. You can use the Davis material for non-associated flow for a wide range of friction angles, particularly high friction angles. We can incorporate pore pressures, which is very exciting for a lot of practical applications, not just slopes, but any sort of foundation or retaining wall problem. I think that FE limit analysis is a vastly superior technique to limit equilibrium. We should be really starting to do away with those techniques. I know that they're embedded in practice, but really there are better methods out there. It's going to take a while because there's a lot of codes out there that use them and a lot of engineers that use them. In the future, we're looking at getting that 3D mesh adaptivity better. It's as I said, the theory is simple, but the practice is not so simple because you can get slivers and disappearing elements. We're working on that. And also incorporating structural elements, plates and shells to model limit state soil structure interaction better. So we look at, we've actually done some work modelling sheet pile walls. I did that with MIT. We've also looking at modelling tunnel linings where you've got metal tunnel linings, which are actually really quite challenging problems. And we can also look at different types of tunnel lining. A lot of acknowledgements, colleagues at Newcastle, other colleagues all around the world. In particular, I'd like to thank John Booker, who's sadly deceased. John Booker was professor at Sydney, is one of the smartest applied mechanics, geomechanics people I've ever worked with. He encouraged me to do these techniques and was really excited by them, and I'm very sorry to see that he wasn't alive to see come to fruition. I'd also like to thank various organisations, and particularly my own university, the Australian Research Council, and a wide variety of industrial organisations that have helped support our centre. Thank you.
Scott has demonstrated how can you really bounce the theoretical and numerical method with practical applications. Now it's question time.
Sorry for the croaky voice. A bit of a struggle. I think they're all hungry.
Yeah, I asked one question. Thanks for presentation. I don't quite understand one part. You highlight the importance of non-associated flow rate. Why can't we just change the parameter by this?
Sorry?
Why can't we just change the phase angle to consider the non-associated flow rate?
Because the limit theorems, if you don't have an associated flow rule, you lose uniqueness. So, you know, when we solve those optimisation problems, the limit load that we get is unique. We know that we don't have that problem that we have in limit equilibrium, where we don't know whether we got the best solution. There's one and only one solution when we solve those optimisation problems. The limit theorems are not applicable to non-associated materials. There are some weak bound theorems that can be established, but the strong bound theorems are only applicable for non-associated flow. So we had to find a way around that. For instance, if you do a lower bound calculation and use the dilation angle as the friction angle, you can show that that's a valid lower bound, but it's often so weak that it's useless because all experimental data seems to indicate that they're way off. So a lot of people have actually worked on that, and that's the reason that it's just that loss of uniqueness. That's the key. And the alternatives give you very weak bounds. The fascinating thing is that we were really surprised when we did that biaxial example that when you find a case where if it's not kinematically constrained, the flow rule has virtually no effect on the limit load. It shows you just how frustrating plasticity theory can be, because you wouldn't normally think that. And as soon as you do nothing else but make the sample shorter, and it has a big effect. So that's the sort of thing we have to deal with in geomechanics. So these methods where you use that Davis approach, because you're always doing you're assuming an associated analysis, you're just using different, C star and phi star, you don't have any problems with convergence, you know you're going to get a solution. And for people in practice, that's a huge benefit, because if they want to look at the effect of a non-associated flow rule, they can do it really quickly and get upper and lower bounds. And all of our data that we've been able to check, and I've got colleagues in Austria who have been working on this a lot with me, have done a lot of practical case histories and got exactly the same. Very, very general and works very well for a whole range of problems. So it's very useful in practice.
Thanks, Professor, for your very illustrative examples. I try to understand when you have to do optimizations to find Actually, the lowest upper bound and the highest lower bound, for example. So how this optimizations looks like? Is a convergence? Is like a quadratic or any kind of?
They're they're good. Yeah, they've got polynomial. They're interior point algorithms, and the number of iterations that it takes to reach the optimal solution is independent of the problem size. So it doesn't matter whether you're solving a problem with 100 variables or a problem with 1 million variables. The number of iterations to get to convergence is the same. Yes. I could give a lecture on. Yeah. But that's not what geotechnical engineers want to listen to is optimization theory. But there are some really smart techniques, and these optimization techniques have only really emerged in the last 5 to 10 years. And the guy called Kakmaka who invented the first interior point, and then other people invented duality gap methods, and these things are really fast. They're really quite quick. And we use the same optimization algorithms. We've got a DEM formulation that uses the same second order cone programming. And you can also solve elastoplastic problems using these methods as well, where you get the optimization algorithm to reduce the virtual work equation. It's quite impressive techniques, but they're not easy to explain.
Yeah, also related to the elements. I would think if you want to get kinematically admissible field, so that's why you optimize the meshes to be finer along the slip lines.
Yeah.
So is it possible this type of philosophy actually applied to other numerical technology like meshless without really locally refining?
Yeah, we do have a meshless formulation for these upper and lower bound techniques, but they do obey the bound conditions except for the boundary conditions, because you can't satisfy the boundary conditions. Yes, so that's the disadvantage with meshless. And sometimes the boundary conditions can be important. We've done a very large 3D upper bound meshless technique, and it works pretty well. But we find that these methods are generally better. And you can also we have a quadratic upper bound element, which we use 6 nodes, and we don't have any velocity discontinuities, and it gives really good results too. You don't have to use velocity discontinuities with that. And I proved that in one of my original papers, that you can use that method and get good upper bounds with that technique. But then you don't have that really nice exact error estimator. That's it's the only nonlinear problem I know where you got an exact error estimate. I wish we had more of them.
Yes. I'm not very good at FEM simulation, so I have a very stupid question. What do you think is the most difficult part in FEM simulation or DM simulation? The complexity of the materials or the models or the algorithms or anything else?
What are the most complex parts of the analysis? Look, I think in geomechanics, we have the worst of all worlds. We've got highly nonlinear materials, large deformations, anisotropy, stress history, discontinuous behaviour. I think that I'm a great fan of doing fundamental research to improve our constitutive models. I think we need to do that, and we need to look at getting models that we can use in displacement finite element calculations or in any other analysis method to get practical solutions. The problem we have is that quite often we can't get the data from the field to use. And most often engineers do know what their strengths are. They have a fairly good idea of the effective cohesion or the undrained shear strength or the friction angle, and they have a fairly good idea of the dilation angle. And if you don't know what the dilation angle is, then using a dilation angle of about a third of the friction angle is pretty close, usually. And Peter Vermeer's got formulas for it. And I think that the problem we have is having really complicated methods and complicated consistency models is, will they get used in practice? And I hope that they do in the future, but we then have to have the data coming from the site to use them. In terms of research, I think there is some incredible complexity. Excuse me. I'll just have a drink. And mostly to do with coupling. And one of the outstanding problems are the solid fluid transition and coupling. Things like debris flow, where you've got fluids and solids moving along together. So they're all very difficult. There's a lot of research in geotechnical engineering. I think it's one of those, it's a great area to work in civil engineering, simply because we have so many unsolved problems, and they're all different. I hope I answered your question.
So you mean once we know all the information about the materials, maybe we can use AI to help us to solve them?
Yes, I think yes. If you want to do fundamental simulations to get better constitutive laws based on fundamental mechanics, I'm all for it. I think it's a good strategy. I talked to Jidong this afternoon where we looked precisely some of those approaches, and I think they're very promising, and I think should be pursued.
Maybe you already answered half of my question. I just wonder, your current method, is it also able to predict large deformation of, say, loose field slopes, or need some coupled with some remeshing technique, or is it already available? Or like what you just mentioned, like debris flow, that's what would be needed for the research, or?
Oh, look, I think for something like debris flow, it flows, then you're really pushing it. But you can certainly do, there's an approach that I've actually had a student having a look at. It's called sequential limit analysis. So you basically analyse a problem, then you get the new problem, which has got deformed coordinates, and do the limit analysis again. So it's basically like you're doing a limit analysis on a series of grids. And people have actually used that to get fairly reasonable estimates of the limit load. The problem you have with all of those approaches is with finite elements you get diffusion. So you end up, as you transfer the variables from one grid to the updated grid, it doesn't automatically satisfy equilibrium, doesn't automatically satisfy the flow rule, and probably doesn't even necessarily satisfy the boundary conditions. So you can end up, after several iterations, solving a problem that's completely unrelated to the problem you started with. So people call it numerical diffusion. For these methods, sequential limit analysis is probably not too bad, because you start off with a new mesh and then you can do it again. And I think I did see a paper fairly recently. I think Chris Martin might have published a paper on look up sequential limit analysis. So that's something that people are looking at, and something we've thought of looking at. We've done work on, for large deformation problems, we've done large deformation finite elements. We've also done material point method approaches, and we've also done a thing called particle finite elements, which is a mixture of continuum and discontinuum. They all work to a certain degree, but they're not. You have to be expert in using them. These are difficult problems. They're super difficult problems. Not yet, not yet. But I think people will get there. I think we will get there. At the moment, I think that's if you're asking me which one is the best, I couldn't tell you. But I know you can do sequential limit analysis to do large deformation problems.
Yes, any questions?
Okay. Another small question. So regarding last one, last part, slope stability analysis involving very high friction angle. So in your example, the friction angle has been as high as 45 degrees already.
Yes.
So in our case, we normally in Hong Kong say we take friction angle normally not more than 40 degrees.
Yeah.
Now, if we take a really high friction angle already, then the outcome in your analysis is quite sensitive to the dilation angle.
Yes.
From 0 to 45.
Yes.
So my questions here are probably two parts. First part, dilation angle might be stress dependent. So
Yes.
if we just take a single value, so how does that affect the result? Second, in our practical analysis, if we just take zero friction angle, dilation angle with very high friction angle,
Yes.
would that result in a reasonable outcome?
Well, if you assume zero dilation angle and you had a fairly localised failure on a slip surface, that's basically going to model the critical state, isn't it? So that's going to be pretty close to the critical state. Now, you only can use that when you do have a fairly large mobilised slip. So I don't think it's going to be any less than that. We typically use, for practical calculations, if we have a dilation angle of around 45, I know that the calculations that we've been comparing with actual slips that have occurred in Austria in alpine gravelly soils, we're typically using dilation angles of around 10 to 15, and they seem to give a fairly good correlation with actual observed failures. Now, it's not answering your question from a theoretical point of view, but certainly the zero dilation does answer it from a theoretical point of view. It's not going to be lower than the zero dilation case, but that might be a bit conservative. That would be my view. Yeah.
Yes.
Is it very difficult to implement the structural elements, or is it just a different strength?
Not that really. We sort of put. My main experience was I did some work with Andrew Whittle at MIT, and we developed some elements for sheet pile walls, and that was pretty easy, not too hard, and the results we got, we compared with measured data, and we got some very nice agreement where they actually had the strength profiles and they had a lot of laboratory data and a lot of in situ testing data, and the limit analysis solutions were pretty good when we put the sheet pile walls in, elements in with realistic estimates for the yield of the sheet pile steel. For 3D, when you're doing plates, anybody who's done 3D plates knows that it's not trivial, structural elements, but I think we could do it. We do have good formulations around that we could put in for to do plates. So if you're looking at, say, a tunnel lining, where you just didn't want to do a simple plane strain analysis and you wanted to model the whole 3D, you'd have to have a curved plate element. And most plate elements that have been published in the structural analysis literature were wrong, because they got the wrong. If you look at the strains in the normal direction, they got the strains wrong. There are only one or two elements that are actually correct. So you've got to be careful, but we can do it. Yeah. And that's not trivial for 3D. Nothing's trivial in 3D, unfortunately. I wish it was.
Okay, and I think it has been a long night for Scott, and as for everyone as well, you probably have a burning stomach now. Okay, And thank you all for coming, and please join me again to Centrifuge for the strong.